Some reactions take place in a single step, but most reactions occur in a series of elementary or fundamental steps. The step-by-step pathway by which a reaction occurs is called the reaction mechanism. We define the reaction order as the sum of the exponents of the concentration terms. Take note that the reaction orders for any single elementary step are equal to the coefficients for that step. In many mechanisms, however, one step is much lower than the others. Take note, an overall reaction can never occur faster than its lowest elementary reaction step. The slowest step is called the rate determining step. The speed at which the slowest step occurs limits the rate at which the overall reaction occurs.
As an analogy, suppose you often drive at a distance of 120 miles at the speed limit of 60 miles per hour, requiring 2 hours. But one day, there is an accident along the road, causing a slowdown. After passing the accident scene, you resume the posted speed of 60 miles per hour. If the total time of this trip was 4 hours, then the average speed will be 120 miles per 4 hours or 30 miles per hour. Even though you drove for many miles at the same high speed, 60 miles per hour, the overall rate was limited by the slow step, passing the accident scene. The balance equation for all overall equation is equal to the sum of all individual fundamental steps, including any that might follow the rate of determining. We emphasize again that the rate law exponents do not necessarily match the coefficient of the overall balance equation.
For the general overall reaction, A of A plus B of B, forward C of C plus D of D, the experimentally determined rate law expression has the form rate equals to constant times concentration of A raised to X times concentration of B raised to Y.
Values of x and y are related to the coefficients of the reactants in the slowest rate determining step, influenced in some cases by earlier reaction steps.
Using a combination of experimental data and chemical intuition, we can postulate a mechanism by which a reaction could occur.
We might later detect reaction intermediate species that are not explained by the proposed mechanism. We must then modify the mechanism or discard it and propose a new one.
Take note that the reaction intermediate is a species which appears in the mechanism of a reaction but not in the overall balance equation.
The reaction of nitrogen dioxide and carbon monoxide has been found to be second order with respect to nitrogen dioxide and zero order with respect to carbon monoxide below 225 degrees Celsius.
Take note, the rate of a reaction involves only the steps up to and including the rate determining step. The overall stoichiometry includes all steps in a reaction. The balance equation for the overall reaction shows the stoichiometry but does not necessarily mean that the reaction simply occurs by one molecule of nitrogen dioxide colliding with one molecule of carbon monoxide. The fact that experimentally determined orders do not match the coefficients of the overall balance equations tells us that the reaction does not take place in one step.
The following proposed two-step mechanism is consistent with the observed rate law expression.
The determining step of this mechanism involves a bimolecular collision between two nitrogen dioxide molecules. This is consistent with the rate expression involving the concentration of nitrogen dioxide to the second power.
In this proposed mechanism, N2O4 or dinitrogen tetraoxide is formed in one step and is completely consumed in a later step. Such a species is called a reaction intermediate.
The gas phase reaction of NO and Br2 is known to be second order in NO and first order in Br2.
A one-step collision involving two nitrogen monoxide molecules and one Br2 molecule will be consistent with experimentally determined rate law expression. However, the likelihood of all three molecules colliding simultaneously is far less than the likelihood of two colliding. The mechanism is believed to be
The NO-Br2 can react rapidly. However, to reform NO and Br2, we say that this is an equilibrium step. Eventually, another NO molecule or reactant can collide with a short-lived NO-Br2 molecule and react to produce two NO-Br molecules as a product. Take note, routes involving only bimolecular collisions or unimolecular decompositions are thought to be far more favorable in reaction mechanisms.
To analyze the rate law that would be consistent with this proposed mechanism, we again start with a slowed rate determining step 2. Estimating the rate constant for this step as K2, we could express the rate of this step as However, NOBr2 is a reaction intermediate, so its concentration at the beginning of the second step may not be easy to measure directly.
We can relate its concentration to the concentrations of the original reactants. Take note, when a reaction or reaction step is at equilibrium, its forward or F and reverse or R rates are equal. Because this is an elementary step, we can write the rate expression for both directions from the equation for the elementary step.
And then rearrange for the concentration of NOBr2. When we substitute the right side of this equation for the concentration of NOBr2 in the rate expression for the rate determining step, we arrive at the experimentally determined rate law expression rate is equal to K constant times concentration of NO to the second power times concentration of Br2.